Hello everyone, I'm Jyun-Jie Liao, and today I'm going to talk about recursive error reduction for regular pension programs. And this is a joint work with my advisor, Eshan Chattopadhyay. So the general topic we are going to focus on in this talk is the randomness versus space problem, which may ask how much does randomness help in space efficiency. And recall that the BPO are the languages that are decided by randomized algorithms that use only log and space, and it is widely conjectured that BPO equals to L, which means every log space randomized algorithm can also be made deterministic using also log and space. And a simple corollary by a padding argument shows that any randomized algorithm that use space s greater than log n can also be made deterministic by paying the constant factor overhead to the space complexity. And before we talk more about this, first let's introduce two very basic definitions. And the first one is the read-once expansion programs, which is a model that captures how the memory of a randomized algorithm changes after reading each random bit. So specifically, a read-once expansion program is a layer graph where each layer in this graph represents the specific time step of a randomized algorithm when we flip a random coin. And then each node in the layer represents the memory configuration of that specific time step, and the edge determine what's the next memory configuration when we see a random bits being 1 or 0. And we can see that on the slides, each edge is labeled with 0 or 1. And also in the last layer, we'll use a label that is either 0 or 1 to represent the final output, so that basically a random walk from a starting state in this read-once expansion program to the last layer would actually simulate the randomized algorithm. And so with this definition, we can see that the randomized algorithm with space S would be can be simulated by a read-once expansion program with the number of nodes in each layer, which we call the width, being W equals 2 to the big O S, and also the length, which is the number of random bits that is read in this layer graph, being N, which is also exponential in S. And the second basic definition we are going to talk about is the pseudorandom generator, or PRG. So we say a function g is a epsilon PRG if it can take a d-bit uniform random seed and output a n-bit pseudo-random distribution that is indistinguishable by function in the specific class f from the actual uniform distribution on n bits. So specifically, it means if we want to approximate the expectation of f on the uniform distribution of n bits, we can simply just take a pseudorandom generator and then enumerate every possible seed, and then take the average on the output of f on the output of g on the seed. So we say d, we call d the seed length of this PRG, and because we are in a space bounded setting, so we say a PRG is explicit if it can be computable in space linear in D. And it's easy to see that if we have a PRG for read-once expansion program with length and width n, then this will imply a trivial space D deterministic algorithm for BPL by simply enumerating every possible seed and take the average of f on the outcomes. So by probabilistic method, we can actually show that there exists a PRG with C length log NW over epsilon, but this is non-explicit, so it does not really imply any generalization results. But if we can make the PRG explicit and keep the C length, then this will trivially imply BPO equals L. But unfortunately, we don't know how to do this. An elegant result by Nissan in the 90s showed that there is an explicit PRG for read-once expansion programs that has C length log n times log NW over epsilon, which is only a log n factor away from the non-explicit PRG. Oh, by the way, the n means the length of the read-once expansion program, and W is the width of the read-once expansion program, and epsilon is the error. And throughout this talk, we will keep this convention of parameters. And although a Nissan generator has been 3 decades old, it still remains the state of the art PRG in the general rewind spectrum programs. And another interesting result I want to point out is a classic result by Sachs and Zhou, who shows that any language in BPL can be made deterministic, can be computed deterministically using only log to the 1.5 space. And the result uses a non-trivial application of Nissan's PRG. So constructing a PRG for rewind spectrum program is actually a really important problem if we care about generalizing bounded space algorithms. And although we don't know how to improve Nissan's generator in the general setting, and it turns out that we can actually get some improvement if we consider some relaxed notion of PRGs. And in this talk, we are going to focus on a relaxed notion called a weighted PRG, which was first defined by Bergman, Cohen, and Garg in 2018. And the weighted PRG is very similar to a PRG, except that now each output of the generator G is also attached with a real weight rho. And if we are trying to use the weighted PRG to approximate the expectation of a function f on uniform distribution, instead of just taking the average of f on the output of G, we will take the weighted average. And an important feature of this definition is that the real weight rho can actually be negative. And it turns out that allowing it to be negative can make this definition surprisingly powerful. And also, even though this weighted PRG is weaker than the actual PRG, it's still strong enough to imply some interesting applications. And so ultimately, the first one is we can, like, by simply enumerating all the C, we can get an approximation of F. And also, a weighted PRG is directly imply a hidden set generator, which is another well-studied variant of PRG that can be viewed as a one-sided arrow PRG. And also, weighted PRG is strong enough to be used in Sachs-Zhou argument that we mentioned in the previous slides. And we'll see that it actually has an interesting implication. So in the same paper by BCG, where they define the weighted PRG, they also show that one can construct the weighted PRG for rewind spectrum programs with C length roughly log n W plus log 1 over epsilon, and with the tilde hiding some log factor. And their original construction was pretty complicated, but it is later simplified and improved in the subsequent line of work. And now we have a very simple construction that has C length log n W plus log 1 over epsilon, which basically removes the hidden log term. And this C length is optimal in the small error regime. And then a really interesting application of this line of work is that Hoza shows that BPL can actually be made deterministic with space slightly better than log to the 1.5. So I think it's only better than Sachs and Zhou's result by some square root log factor, but it's still an improvement over a decade-old result. And it's basically by plugging in a proper weighted PRG into the Sachs-Zhou argument. And we have seen that Sachs-Zhou argument actually can also be applied on weighted PRG. So this basically justifies that weighted PRG for rewind spectrum program is also an important object to study. And I also want to point out that some weighted PRG in the most recent works are basically a black box reduction from weighted PRG with very small error to PRGs with like moderate error, where here moderate means 1 over Polian error. And also the black box reduction roughly looks like we take the big rewind spectrum program and then we break it into several blocks. And then we will approximate each block using the base case PRG G0, and then we will take some linear combination of those blocks and then do some denomination. And it turns out that a proper choice of decomposition would make the blocks like align and cancel very well, so that the error of the base case PRG actually combine in our favor, which led us move from a moderate error in the base case to very small error in the final weighted PRG. And also, I want to point out that so throughout this talk, we will take the generalization part for granted and only focus on the decomposition part. And the decomposition part in the previous work mainly used the Richardson iteration, which is a technique that is borrowed from spectrograph theory. And this will give a number of blocks being roughly log 1 by epsilon divided by log 1 by epsilon 0, which is good enough to imply the really good C length after generalization. And we have seen that in Nissan's PRG, if we relax our notion from PRG to weighted PRG, then we can remove the log n factor from the log 1 by epsilon term in Nissan's PRG. So it's natural to ask if we can also get any improvement over the first two terms. And although we don't know how to do this in the general case, it turns out that if we focus on some restricted setting called regular Riemann spectrum programs, we can actually get an improvement in the first term and even for PRG. So a regular branching program, and recall that a branching program is a layered graph where every node has out degree 2, and we say it is regular if every node has in degree also being 2. And although this is a more restricted setting, it turns out that it's still general enough to capture the general branching program, which means if we have any length n with W branching program, then it can actually be reduced to a regular one with the same length and the width blow up to NW, as shown in a recent work by Li, Pine, and Vadan. And also, and for this restricted setting, a really nice result by Perverman, Rao, Ross, and Yahudiov in 2010 showed that there actually has a explicit PRG for regular Riemann spectrum program with C length basically removing the log n factor from the first term in Nissan's PRG. And another exciting work, more recent work by Ahmadinejad et al. Show that if we only care about like white box generalization, where we can see the whole branching program, then for regular branching program, we can approximate the random walk probability from a node to another node, use like almost optimal space, and even for very small error. So given the really nice PRG for regular branching programs, it's natural to ask whether we can also get a better weighted PRG for regular branching programs by just taking the base case to be the PRG in BRY. And it seems quite trivial, but it actually not as trivial because the reduction in previous work actually required the epsilon 0 to be less than 1 over n. And so in this regime, basically BRY has no improvement over Nissan's PRG. So by taking the base case to be the BRY PRG does not mean we get any better weighted PRG over the general case. But it turns out that this issue can actually be resolved, and it was also recently resolved by Chen, Hoza, Liu, Tao, and Wu in Fox 2023. And they basically show that in the regular setting, we only need the base case error epsilon 0 to be smaller than 1 over pi log n. So as a consequence, they get the following theorem. So the first theorem is there is a weighted PRG for regular Riemann spectrum program with the C length as shown on the slides. And this C length is actually better than the weighted PRG for the general case when we are in a small width moderate error regime. And the second theorem is they show that with the similar idea, they can actually get a simpler proof for the white box randomization result that we mentioned a few slides ago, which shows that we can like approximate the random walk probability in the regular branching program in like almost optimal space. And like the first proof by like Ahmadinejad et al. Used like very complicated spectral graph theory machinery, but in the work by Chen et al. They show basically get a simpler proof that has like more similar spirit to BRY. And our main contribution in this work is that we show that there actually has an even simpler proof for both results. So before we talk about our result, first let's briefly review what's the conceptual takeaway of the result by Chen et al. So they basically show that if we are in the regular settings, then the idea in BRY can not only help improve the base case, but can also help improve the error reduction part. And there are some main ideas in BRY which we list below. And the first one is that the approximation error of some specific choice of PRG can be made proportional to the amount of mixing, which roughly means like how much do we get closer to uniform after making the random walk following the rewind spectrum program. But unfortunately, we don't have time to define it formally. And the second property is that the total amount of mixing will be bounded if we are using a regular rewind spectrum programs. And this is also probably the main point, the main place where we require regularity. And then the third thing is the above two properties would imply a more efficient error bound in PRGs if the PRG is constructed in the binary recursive way, which is roughly looks like follows. So suppose we want to get an approximation for a really big rewind spectrum program A, then what we do is we will divide the spectrum program A into two parts, and then we'll approximate the first half and the second half recursively, and so we get B1 and B2, and then we'll take the combination of B1 and B2 and then approximate it to get our final approximation A. And given the previous two properties, if we can prove that the total error in each layer is proportional to the total mixing, and also with regularity, if we can show that the total amount of mixing is bounded, then this will show that in this recursive procedure, the final aggregated error is proportional to log n times the total mixing, which will be better than the general case. So this is a very vague but with the high level ideas. And so given these high level ideas, the implementation by Chen et al. Is basically like they try to embed a binary recursive like structure into the prior error reduction that are based on Richardson iteration. And then to prove their two theorems, they need to choose proper definition of amount of mixing. And the first for the first theorem, which is a weighted PRG for regular rewind spectrum programs, the amount of mixing is defined the same as the weight in BRY. And for the second theorem, which is the white box generalization, the amount of mixing is defined using the singular value approximation that is introduced in the recent work by Ahmadinejad et al. And with these ideas, they can get a desired error with proper choice of base cases and some proper potential arguments. But probably because the Richardson iteration does not like is not naturally binary recursive, so it turns out that their final analysis is still somewhat tricky and requires some non-trivial ideas. So the main contribution of our work is we show that we can like keep the same definition of amount of mixing, but we will instead apply the conceptual ideas in an alternative and actually binary recursive error reduction. So we don't need to like force some like binary recursive reduction to something that is not originally binary recursive. And the analysis turns out to be rather straightforward if we do this. And to see how our reduction work, we first briefly recall how the rewind spectrum program correspond to a random walk matrix, where for a rewind spectrum program, we will use a matrix to with the entries denote the probability of getting from one node to the other node by taking a random walk. So with this definition, we will see that concatenating the random walk basically correspond to like doing matrix product. So with this matrix definition, let's see that if suppose we have a really large like a really large branch program, and then we want to approximate it with small arrow, and it turns out that the like our prior work that simplifies the result in BCG can also be viewed as an error reduction procedure that works as follows. So let's say we divide the branch program into two halves, A and B. And for A, we have like AI being some like epsilon 0 to I plus 1 approximation of A. And similarly for B, then in our prior work, we defined like a recursive error reduction formula. That is, we write the kth level approximation of AB as the sum of AIBJ, where I plus J equals to K, minus some other AIBJ. And the claim is that by doing this, we can also show that this ABK is also epsilon 0 to the K plus 1 approximation of AB, so that the inductive hypothesis can go through. And for K equals 0, we will just take the base case PRG and get an epsilon 0 approximation. And so the reason why this error reduction formula works is because of the following identity, which basically breaks the error of ABK into some product of error of AIBJ and the actual like exact matrix A and B. And one can observe that given the guarantee that AI and BJ are good approximations, this will imply that ABK is also a good approximation. But because like we get that is a good approximation that has like error epsilon 0 to the K plus 1, but times some extra constant factor. So after log n level, this error blows up. And then this means like after log n level, we get a poly n error blows up. So the bottom level error should also be 1 over poly n. And this is not ideal because we want to take the base case to be the BRY PRG, and we want it to have allow it to have larger errors so that we actually get saving over Nissan's PRG. So our idea is to explore regularity in this proof, and then specifically, let's say we have some MAMB being denoting the amount of mixing in part A and in part B. Then our inductive and consider our inductive hypothesis to be that AI gives the epsilon 0 to I plus 1 approximation, but also this is proportional to the amount of mixing of A, like which is MA. Then we get that in the last two terms, we can see that the first term is like upper bounded by epsilon 0 to K plus 1 and MA, and similarly the second term. So we get that the sum of the two terms is upper bounded, is also proportional to the amount of mixing of MAB, and it remains to show that the sum of like the terms in the first two summations does not ruin this analysis. And so how we do this is by observing that each term in the first two summations are like product of small error matrices. So we take our inductive hypothesis to be like, we make sure that we divide the whole thing by an extra factor denominator D instead. And so that if we have like two matrices multiplied together, then we'll get an like 1 over D squared denominator. And this is like much less than our target error. And it basically would show that the ABK is like basically close to what we assume in the inductive hypothesis when multiplied by an extra 1 plus 1 over D factor. And because this lasts for log n error, so it turns out that, oh, sorry, this is blocked. So taking D to be log n actually suffices. And so by like going through analysis, we will see that this allows us to also take the base case error to be polylog n, and everything goes through. And like the actual analysis where we like put in the actual definition of amount of mixing would also be really trivial in this like outline of proof. So finally, we want to give some final remarks. So first, to prove theorem 2, we'll use a different recursive formula that implement the same matrix more space efficiently. And it's not the same binary recursive formula that we see in the previous slide. But in the analysis, we still use the binary recursive formula. And it turns out that this alternative recursive formula shows that our binary recursive construction is actually equivalent to the Richardson iteration-based construction by Chen et al. And we found this really surprising because the two analyses is very different. They seem very different, but they are actually equivalent. And finally, let me show the conclusion slides. And that's it for today's talk. Thank you for listening.